15 seconds. That's how long you'd stay conscious if you were exposed to the vacuum of space with no suit, no warning, no second chance. Your blood doesn't freeze. It boils, even in the cold of space, because pressure drops to almost nothing, and the liquids inside you start turning to gas. Your skin doesn't explode, but it swells, sometimes to twice its normal size, stretched tight like a balloon left out in the sun too long. And the whole thing happens in near total silence, because there's no air left to carry the sound of your own scream. Ever tried holding your breath at the bottom of a pool, counting the seconds until your lungs start burning? Multiply that panic by 10. Take away the water, take away the air, and you're somewhere close to what 15 seconds in raw space actually feels like. But this, as brutal as it sounds, is only the opening chapter of what space can do to a human body. What comes after gets stranger, slower, and in some cases, almost impossible to picture surviving even in theory. Start with something quieter. No explosion, no violence, just air slipping away. A slow leak in a suit or a cracked seal on a station module can drop oxygen levels so gradually that you don't even notice you're dying. Your judgment goes first. Simple tasks start feeling foggy, like trying to think clearly after being awake for 2 days straight. Then your vision narrows, the edges going soft, and somewhere in that fog, most people don't even realize they're suffocating. There's no clawing for air, no dramatic gasping like in the movies. Just a slow drift into unconsciousness, the way you might nod off during a boring lecture, except you never wake back up. Astronauts train obsessively for this exact failure, because it's the kind of death that sneaks in through the back door while your brain is busy convincing you everything is fine. Now, push the temperature to its extremes, because space doesn't really have a climate. It has two brutal opposites sitting side by side. Step into direct sunlight without shielding, and surface temperatures on your suit can climb past 120 degrees Celsius, hot enough to warp exposed metal. Step into shadow just a few feet away, and the same suit can plunge below negative 100 degrees Celsius in minutes. Picture standing with one hand in a hot oven and the other in a deep freezer, except in space. Moving a few steps in any direction can flip you from one to the other instantly. There's no gradual afternoon here, no gentle sunset cooling things down. Astronauts describe the sensation as living inside a switch that's constantly being flipped. And if a suit's insulation ever fails at the wrong moment, the human body simply isn't built to handle either extreme, let alone both back to back. If you're already picturing yourself out there, here's the uncomfortable part. Imagine you're on a spacewalk right now, tethered to a station, and a piece of debris smaller than a coin punches through your suit. You wouldn't hear it coming. Space debris and micrometeorites travel at speeds up to 28,000 kilometers per hour, fast enough that a fragment the size of a grain of sand can punch clean through aluminum plating like it's paper. There's no time to react, no warning shot. The impact itself might not even register as pain right away, because the real danger isn't the hole, it's what happens in the seconds after, as your suit's pressure starts bleeding out into nothing. Engineers actually build extra shielding layers into suits and station walls specifically because of this, treating something the size of a pebble as a genuine threat to an entire mission. If you're finding this as unsettling as I do, go ahead and subscribe now, because the danger is about to stop being physical and start coming from somewhere you can't shield against nearly as easily. Radiation is where space stops playing by any rules the human body evolved to expect. Beyond Earth's magnetic field, astronauts are hit with cosmic rays and solar particles that can pass straight through spacecraft walls, through skin, through bone, damaging DNA at a cellular level with every exposure. A single strong solar flare can deliver more radiation in a few hours than a person would normally absorb in several years on Earth. Here's a strange way to feel that scale. Some astronauts have reported seeing flashes of light with their eyes closed, in complete darkness, because high-energy particles were literally passing through their eyeballs and triggering the optic nerve directly. That's not a hallucination, that's radiation writing itself onto the inside of a human eye. And if this is what unshielded particles do quietly, in the background, picture what happens the moment the sun stops being subtle about it and unloads that same energy all at once. Because now we leave the astronaut suit behind and start talking about entire spacecraft. A powerful solar storm, a coronal mass ejection, can send a wave of charged particles slamming into a ship's electronics, frying navigation systems, life support controls, and communication arrays within minutes. It's happened before on a smaller scale, knocking out satellites and power grids on Earth. Now scale that same storm up and point it directly at a crewed mission with no planet-sized magnetic shield to hide behind. Every backup system, every redundancy engineers built in, could fail at once, not because of one single point of damage, but because the entire electrical nervous system of the ship gets scrambled simultaneously. It's the difference between losing one light switch in your house and losing every wire behind every wall at the same time. Then there's the quiet horror of simply drifting. No explosion, no fire, just a broken engine or a severed tether. And suddenly, you're moving away from your ship at a slow, steady drift with absolutely nothing to grab onto. There's no current to swim against, no ground to push off from, just an unbroken silence stretching outward in every direction. Death here doesn't come fast. It comes over days, as oxygen runs low, temperature control fails, and the body slowly shuts down, while the mind has nothing to do but watch the ship and the possibility of rescue shrink into a point of light. Try sitting in complete silence for even 10 minutes with your eyes closed, no phone, no sound, nothing. Now imagine that silence stretching for days, with your own thoughts as the only company you have left. Supernovae. Take the danger and multiply it by an entire star system. When a massive star runs out of fuel and collapses, it can release more energy in a few seconds than our sun will produce in its entire lifetime. A supernova going off within roughly 30 light-years of Earth could strip away enough of the atmosphere's protective ozone layer to expose the surface to lethal radiation, potentially wiping out complex life across an entire planet. That's not science fiction. That's a documented mechanism scientists believe may have contributed to mass extinction events in Earth's own deep past. Picture a streetlight blowing out with enough force to shatter windows for miles around, then scale that shockwave up until it's measured in light years, instead of city blocks, and you're only beginning to approach what a nearby supernova actually represents. Neutron stars push things further still, because what's left after a supernova can be almost impossibly small and impossibly dense. A neutron star can pack more mass than our entire sun into a sphere roughly the size of a city, spinning hundreds of times per second, wrapped in a magnetic field trillions of times stronger than Earth's. Get anywhere near certain neutron stars, particularly the ones called magnetaires, and that magnetic field alone could rearrange the atoms in your body before radiation even finishes the job. Scientists have calculated that a magnetaire's magnetic field at close range could distort molecules on a level that essentially reshapes matter itself. A teaspoon of neutron star material would weigh roughly 1 billion tons here on Earth, heavier than every car ever manufactured combined. And even that staggering density is still not the most extreme thing hiding out there in the dark, because nothing on this list compares to what happens near a black hole. As you approach the event horizon, the difference in gravitational pull between your head and your feet becomes so extreme that you'd be stretched, thinned, and pulled apart into a long, thin stream of matter, a process scientists actually call spaghettification. And it's not an exaggeration, it's the literal physics term. Around a smaller black hole, this stretching would happen violently within seconds, well before you ever reach the point of no return. Around a supermassive black hole, the stretching is gentler at first, meaning you could theoretically cross the event horizon still intact, still alive, watching the entire visible universe compress into a single point of light behind you, with absolutely no way to send word back about what you saw. That thought alone, crossing a boundary the universe itself may have no way of letting information escape from again, is one of the strangest and most unresolved questions in modern physics. And that's really where this list has to end. Not because we've run out of danger, but because we've run out of certainty. Beyond the event horizon, our physics runs out of answers. Nobody knows, not really, what happens to matter, or information, or anything at all once it crosses that final line. Some physicists argue it's destroyed. Others argue it's somehow preserved, scrambled into radiation that leaks back out over unimaginable stretches of time. It might be the single strangest way anything in this universe can end. Because it isn't really an ending at all, it's a question mark, sitting quietly at the edge of everything we understand, waiting for someone to eventually answer it. If this kept you hooked until the very end, that's exactly what I was going for. So go ahead and subscribe if you haven't yet, drop a like on your way out, and let me know in the comments which one of these actually got under your skin the most.